Welcome to video tutorial of mechanisms by mekanizmalar. In the video of horizontal axis wind turbine we talked about two important control mechanisms for the wind turbine. Yaw and pitch control. The yaw control mechanism turns the nacelle of the wind turbine in such a way that the rotor always faces the wind. This is easy to understand. On the other hand, the pitch control, which rotates the turbine blades around the blade center line, whenever wind speed changes, is hard to understand. Why the blade should rotate around blade center line when the speed of the wind changes? The airplane wing and the wind turbine blade work with the same aerodynamic principle called the lift. Anytime the air flows around an airfoil-shaped object, the lift is generated due to Bernoulli laws. This lift makes the airplane stay in the air and make the turbine blades to rotate. If airplane wings and the turbine blades are working with the same principle, then why the airplane wings are straight and the turbine blades are twisted? To answer these two questions we should understand the concept of the relative velocity and the velocity triangles. Do not get scared. We are not going to talk about Einstein's relativity theory. The engineers design the airfoil, whether it is airplane wings or turbine blade, such that the relative flow velocity is always tangent to the airfoil in a given cross-section. Let's emphasize this one more time: the relative velocity of air should be always tangent to the airfoil profile. Blades would fail catastrophically if relative velocity is not tangent, or almost tangent to the relative velocity. So what is a relative flow velocity? Assume three green cars in the highway traveling with the same velocity but at different directions. And you are driving a yellow car as shown in the figure. We will call you as observer from now on. Now assume that all the cars' speed is 50 miles per hour in a given time. As far as observer is concerned, the speed of the car following the observer is 0, because both cars are traveling at the same direction with the same speed. This is easy to understand for anyone driving a car. What if another car is approaching to the yellow car from the front with same speed? What will be the relative velocity of that car with respect to observer? Since both car travels with same speed, but in opposite direction, it will be 100 miles per hour. We also experience this on the highway and it is easy to understand. How engineers find the relative velocity of approaching car? They find the relative velocity by joining the arrowhead of the approaching car velocity with the arrowhead of observer car velocity. Then they draw a vector from the base of approaching car velocity to the base of the observer's car velocity. In this case, base of vectors shown by circles. The newly drawn red arrow is the relative velocity of the approaching car. Now assume that the observer's car approaching a 90-degree crossover road with 50 miles per hour speed, and another car approaching toward the same junction with the same speed. What will be the relative speed of the approaching car with respect to observer? Now that is not that easy to find the relative velocity of the approaching car. Now let's apply engineering solution to this problem. First we will join the head of approaching car velocity vector to the observer velocity vector. Then draw a vector from the base of the approaching car vector to the base of the observer car vector. The triangle formed here is called as the velocity triangle by engineers. The relative velocity in this case shown as inclined red vector. This inclination of the relative velocity causes the turbine blade to be twisted, and we will explain how. Since the turbine blade rotating perpendicular to the wind direction, this is exactly similar to the last case we described where the car was approaching to the observer from a side road. However, there is some slight difference. When the blade rotates around the turbine axis, the observer velocity shown by green will be different at each point of the blade. Further away from the axis, the faster the velocity will be. The velocity triangles are shown in 5 different parts of the turbine blade. Notice that while the wind velocities shown by blue arrow are the same in all 5, the green vector gets larger when the profile is away from the rotation center. This changes the looks of all 5 velocity triangles. As you can see, the blade profile is shown as tangent to the relative velocities. When we superimpose all these profiles one top of another, it takes a twisted shape. When the wind speed change, the velocity triangles also changes, as you can see. This means that we should have different blade shape for all the different wind velocities. It is almost impossible to build a blade which morphs itself to new shape for changing wind velocity. The solution is the pitch control. Engineers design the blade profile in one specific wind speed, say 15 meters per second. Then they assume that the middle point of this blade should always work at optimum condition at that point. In operation, rather than morphing the blade shape, the pitch control allows very close approximation to this desired shape. The pitch control will allow the design point, which we assumed as the middle of the blade, operate at optimum speed in any given wind speed. There will be small deviations on the other points of the blade when the wind speed goes away from 15 meters per second, but these deviations are negligible. This can be observed by comparing the angle of airfoil with angle of the red arrow. You should also notice that when the wind speed is low, the blade shows the maximum R to the wind. When the wind speed approaches to the upper limit of the operation, the blades show minimum area to the wind. If the wind speed increasing further, blades should be brought up a configuration that it reduces lift effect on blade and least resistance to the wind. Also, brakes should be activated so that rotation of the blades forcefully prevented. Thank you for visiting mekanizmalar channel and watching our videos. If you enjoyed this video, please give it a thumb up and subscribe to our channel.